Welcome back. In this lesson, we're going to look at the Bowen series. N.L. Bowen was a geologist that lived during the first part of the 20th century, and he studied magma. And as magma cools down, he found that certain smaller crystals will come out and crystallize out of the solution first, and that the larger crystals will take a cooler temperature in order to crystallize. So as these minerals crystallize out of the magma, you can form different rocks. Also, as those crystals come out of the magma, the composition of the magma changes, and whatever's left over, you end up with different types of rocks. So inside a magma chamber that would cool completely down, you could have various types of silicates. We already know that most of the rocks on Earth are silicates, which means that most of the rocks on Earth at one time had been magma. So depending upon what the structure of those rocks are, has a lot to do with how fat or how high the temperature was when the crystals crystallized out of the magma, and whether or not they reacted with the other minerals that were in the melted magma to form different types of rocks. So let's take a look. So the question I would have, if you have one type of magma and you've got basically a soup with some kind of a recipe of rocks melted all together and all mixed together, how can you have different rocks come out of that same stuff? So if you remember what we've done in class, if you have a single tetrahedron, silicate tetrahedron, the representative rock of that is olivine. Then if there's a double pyramid, okay, so instead of just a single tetrahedron, you've got two of them joined, then you will have the pyroxene, and then it just keeps getting more and more complicated. The two will join into a chain, and you can have a chain, and then you have the amphifold, and then from there you can have double chains and rings and sheets and three-dimensional structures. And each one of these larger structures of silicates cools at a lower temperature. So the first one to cool, if you have a huge magma chamber and the heat has been removed in some way so that it starts cooling down, it never came out as lava, but it's starting to cool down again, then the first one to crystallize will be your olivine because it's the simplest structure. Then after that, the pyroxene, and then it just continues moving to the larger and larger. The largest structures, remember the three-dimensional structures, was the quartz. You also have the different minerals that are in that soup that come out with the different minerals. So you have different metals or whatever that's combining with these minerals as they're coming out. So essentially, along the edges, if you were cooling down a huge bucket of chocolate, along the edges of the pot that become cooler, that's where the chocolate is going to start crystallizing. It's going to be liquid in the middle and harder and harder and harder on the outside. It's exactly what would happen underground. If you had a magma chamber and all of it's melted, and then you removed the heat, so the heat source has been moved to some other place, then as it cools, along the edges, some of those minerals are going to start crystallizing. The first to crystallize are the smaller ones, and the last to crystallize are the larger ones. So then you've got the soup pot that's still melted is getting smaller and smaller and smaller. So whatever temperature, two or three different minerals come out at the same temperature, you can find those minerals in the same rock. If you, for instance, if feldspar and quartz and mica can all be in granite because they all would come out at about the same temperature. But olivine, which would crystallize first, and quartz, which would crystallize last, you would never expect to find both of those in one rock. Now this is called the Bowen's series. And N.L. Bowen was a geologist in the early 20th century, and he was the first to look at this cooling magma and make some remarkable connections. First of all, he realized that as the temperature is cooling down, the simpler silicates will come out first. They will crystallize first. So the first minerals you should expect to see is olivine. And then as the temperature drops down, you can get others and others. But more is happening than just the temperature dropping. Okay, so pyroxene, it takes if it's too hot, it won't crystallize. It has to be cool enough for the pyroxene to come out, and then cooler enough for the amphibole to come out. But what is more interesting is that let's imagine that the crystal doesn't go along the edge of the pot, okay, of the magma chamber, but instead it crystallizes inside the melted soup. Okay, so let's imagine I've got a crystal of olivine and it's hanging out in the middle of the magma chamber. It's still a crystal, but it's able to crystallize at a higher temperature, and then as the temperature drops down, it just continues to float there. Well, that olivine can react with other tetrahedron silicates in the magma and become pyroxene. So the olivine can join up and make doubles, and then the doubles could be could form chains, and then the chains can form rings, and the rings can form sheets. So lots of things can happen. So one chemical can actually react with the soup and become a bigger chemical, or a mineral, become a bigger mineral. So these minerals will start coming out at cooler and cooler temperatures. Now, the Bowman's reaction series actually has two sides. You have the pure silicate side, which is olivine, pyroxene, amphibole, biotite. Then you're going to have the feldspar group. So the right-hand series is really calcium rich. So it's not just silica and oxygen. It's not just silicon and oxygen, but it's also some calcium. And so you're going to get what will eventually be the feldspars. And if you remember, the feldspars are about half of all the rocks in the Earth's crust. Well, as you cool down, the calcium feldspars will come out first, and then eventually the sodium feldspars will come out last, and then the potassium feldspars will come out when it's even cooler. So as it comes down farther and farther, you're going to get some feldspars coming out at the same time that you might have some pyroxene come out, at the same time that you're going to get some amphibole coming out. So two different types of rocks can be produced by the same pot of liquid rocks.